In this session, we are going to be exploring something called the derivative. This is the backbone of Calculus 1. But first, to gain an understanding of what a derivative is, we are going to focus on something called frame of reference to get an idea of what a derivative actually means. So picture yourself standing on the sidewalk outside. If I'm standing on the sidewalk, the ground itself might look flat. But if I instead were sitting on the moon, the ground, or I wouldn't be able to see the ground that I was standing on necessarily for the sidewalk, but I know looking down at Earth, I can tell that Earth is actually round. So the ground that I am standing on right now might seem flat, but in reality it is not. We can call this our frame of reference or our point of reference. So we're going to use this same idea with functions to talk about something called the derivative. And specifically, we're going to name that the local linearity. And what that means is if I took a function and I were to zoom in on it, it may start to take the attributes of a flat line. So for instance, if you were to think about the equation y equals x squared, we know that that is a parent function for all the quadratic functions. And if I were to pick any point on this graph and I were to zoom in on it, so let's pick a point. Let's say this point right here. In my calculator, if I were to zoom in and keep zooming in, my window would, if my point was here, would start, it would look curved, and it would gradually, the more and more I zoomed in on it, become something that looks straight. So if I could figure out the slope of this line, which we in Algebra 1 know that slope is y2 minus y1 over x2 minus x1, I could talk about an instantaneous rate of change at this point. So if this function were to represent the position of a bicyclist or something like that, I could find the slope at this point and I would know how quickly the bicyclist was going at that point. This is kind of the backbone for what a derivative is. It is simply looking at a rate of change, whether it's in context or not. Any function, I can find an average rate of change or an instantaneous rate of change based on what information I am given. We call that the derivative. Okay, so let's look at another function. I want you to look at f of x equals absolute value of x plus 1. So we've already explored y equals x squared, so I'm just going to redraw that. And I want us to first compare this to the absolute value of x plus 1. So that is the absolute value function that looks something like this. It has its vertex at the point 0, 1. And it is linear on either side. So the local linearity for this one's not very interesting at any point other than its vertex because it's already a line. But at the vertex, if I were to zoom in on this, okay, so if I were to zoom in at this point right here, the question is, does it take on the same shape, the same linear looking shape, the more and more I zoom in on it, like our y equals x squared? So if I zoom in, it looks like this. If I do it again, it still looks like this. No matter how many times I zoom in, I get the picture to look like a V. And so what this means is that a derivative can only happen or only exist if I were to zoom in on that point and it were to take on a linear look. So because this one does not take on a linear look, we would say that that particular point itself does not have a derivative. It doesn't exist. Anywhere else on this graph, if I zoomed in, say over here, it's already linear. So it would take on a linear local linearity look, but the vertex does not. So we have some stipulations for this idea of an instantaneous rate of change, aka our derivative. It has to be for the function, whatever point that we're looking at, it has to take on an appearance of local linearity as I zoom in closer and closer and closer to that point. So there's lots of different options. Okay, again, I kind of drew this, in this case, a y equals x squared plus 1 could be for this graph, a basic graph. I just shifted our parent function up 1. So at any given point, okay, we can zoom in on it to find the slope of the part that when it starts to look linear. And what's happening is as I get closer and closer, as I zoom in closer and closer to this point, and it takes on the linearity, we can find this slope to find the value of our derivative at that point. So to take this a step farther, our derivative is going to be the slope of the tangent line at a point on the graph. So when I take the derivative, if I'm just doing the derivative of a function, I'm going to get out something that represents all of the possible tangent line slopes. If I plug in an actual x value, I will find out the slope of that particular tangent line. So this tangent line, remember, a tangent line is a line that touches a curve at one point. Okay, so I've drawn 3 different ones onto this picture. Okay, so if I'm on the side to the left of our vertex, these slopes are all going to be negative, and depending on which point I choose, the tangent line will have a different slope. It's steeper the farther away from the vertex I go to the left, and gets shallower as I approach the vertex. When I get to the vertex, I notice that I have a horizontal tangent line. That means the slope of that line is 0. So the slope of our tangent line to the right is all going to be positive, and they get steeper the farther away from the vertex I go. Depending on your function will determine what kinds of slopes that I have, okay, positive, negative, how steep they are, and so on and so forth. So now we need to think about, well, okay, how can I describe and determine these actual slopes algebraically? So I have a curve here. It doesn't really matter what the curve is. And I am going to picture the point that I want, the point that's in question. Okay, so this is the point that I want the instantaneous slope for. So I know the only way I can find the slope in terms of local linearity is to have 2 points. And I'm going to take y2 minus y1 over x2 minus x1. So if I have y2 minus y1 over x2 minus x1, then I can find a slope. The problem is if I'm using tangent line, I only have 1 point to choose from. I can't use necessarily an actual tangent line then in order to do this. I'm going to draw a secant line. Okay, so this secant line means that it's a line that crosses the curve in 2 places. So if my point here is some value, we're calling it, I might call it x comma y, and I might call this other point that I draw in here to get my secant line, they have it listed as c, f of c, I might call this x plus delta x, and y, f of x plus delta x. Okay, and you'll see why I'm doing that in a second. So if I were to find the slope between these 2 points, okay, so now I'm going to do my y2 minus y1 over x2 minus x1. I'm going to get y2 minus y1. So I'm going to call this y value f of x, okay, just for continuity. And then I can take my x2 minus x1. Simplifying this, I can't really do anything with the top. Okay, so what this gives me then, so I have my f of x plus delta x minus f of x minus delta x. This delta x just simply means a little bit of change. I'm going to pick a point on the curve for my secant line that is very close to the point that I actually want. So that delta x just represents the little bit of change that I moved over to get my second point, and then when I plug it in, I'm going to get a slightly different y value so that I can actually find a slope between these 2 points. The problem I have here, though, is when I'm not actually finding the slope of the tangent line. I'm finding the slope of the secant line. We would call this an average rate of change. And I always call that AROC, average rate of change. We don't want an average, we want an instantaneous rate of change. So, what I'm going to picture then is this second point that I chose, the x plus delta x, comma, f of x plus delta x. I want to picture this sliding down the curve towards the point that I want the instantaneous rate of change for. So basically what we're looking at is as this change horizontally goes to 0, what is this going to do? What does the slope become? So the idea of sliding these 2 points until they're on top of each other, we call this a limit. And we learned about limits in a previous chapter. So what is the function, or what is the function doing as I approach a certain x value? So now we get our slope, we're still calling it m right now, y2 minus y1 over x2 minus x1, becomes a limit, and we want as that change in x. So as this point up here slides down and is going to become 1 and overlap the point that I actually want, what is my slope approaching? So I'm still going to use f of x plus delta x minus f of x. There's my y2 minus y1. And then when I did my x2 minus x1, it was x plus delta x minus x. So ultimately my slope is the limit as these points slide down so that they are on top of each other, and it becomes my f of x plus delta x minus f of x all over delta x. So algebraically I can put this in, okay, and it will give me the ability to algebraically solve. Now we know that if I plug in 0, or for a limit, we're going to plug in 0, see what happens. If I get 0 over 0, then I know algebraically something must cancel out, and then whatever I'm left with, I can plug 0 in again to get at my actual limit. So this in turn, is our definition of a derivative. Okay, a derivative is the slope of the tangent line of a curve at any given point on the curve. So that gives us a rate of change, and later on you will find out what ways we can use that idea of rate of change. So I'm going to do one real quick example for you to apply the definition of a derivative in video B.